Hey everyone, and welcome to Lecture 8. Today will be a review of the course broken into two parts, Part 1 and Part 2. The listening assessment for the week will be drawn from this lecture, as well as Checkpoint 8. So let's start with sound. Sound is a physical disturbance, vibration, or oscillation. It involves molecular displacement and mechanical transfer of energy through a medium. It's made up of two different parts: the compression, which is an area of increased pressure that forces particles of a medium closer together, and rarefaction, which is an area of decreased pressure that forces particles of a medium further apart. The equal loudness contours demonstrate the nonlinear function of the auditory system in regard to amplitude and frequency. To plot this out, Fletcher and Munson designed the Fletcher-Munson curves in Bell Labs in 1933, and they demonstrate the nonlinearity of our ears, or that we do not hear all frequencies equally. Now, even though we don't hear all frequencies equally, we do have a frequency range that we are quite confident with. So the frequency range of the human ear is generally 20 Hz to 20 K. In terms of amplitude, the dynamic range is actually pretty wide. It goes from 0 dB, which is the quietest sound you can imagine, all the way up to 120 dB and above, really. So in one of your first quizzes, you had to identify frequencies. So we're just going to go through and play some frequencies and see if you can guess what the frequency is. This first one. It's 500 Hertz. Second one. 1K. Third. 2K. $4K. And last, that's miserable. So at about 120 dB, there is something called the threshold of pain. It's dependent on frequency and dependent on individual sensitivity of the listener. While we typically start to feel pain at 120, for some people it's actually closer to 140 where they start to feel that pain. Let's review level changes in music. We'll start with the reference level. Now with plus 5 dB of gain. Now with plus 5 dB of gain. Now with plus 10 dB of gain. Alright, let's listen to the reference file again. Now with minus 2 dB of attenuation. Minus 5 dB of attenuation. And now minus 10 dB of attenuation. Frequency and pitch have a nonlinear relationship. Frequency is measurable, where pitch is subjective. Frequency does not change with amplitude, whereas the pitch, there can be perceived changes with amplitude. With frequency, this does not suggest harmonic content, but with pitch, there is the perception of fundamental as well as harmonic. Masking is the amount by which the threshold of audibility of one sound is raised by the presence of another masking sound. What that means is that when two or more sounds are playing at the same time, one or more may be obscuring another sound. It does this in two ways, through amplitude and frequency. When I was doing labs on campus, sometimes I would ask the students to demonstrate masking, and that's all I would tell them. Sometimes they would get a sound and then use an EQ to drop the frequencies. Now, this is not masking. That would be like going to a masquerade ball, but instead of wearing a mask, you cut your nose off. And yeah, it's painful and not really what they were asking for. So, noise is random particle displacement. Noise can take on many forms: clicks, pops, hums, or any sound that is not intended to be a part of the recording. Other types of noise include analog or digital equipment, tape hiss, and analog recordings, quantization errors, 50 or 60 Hz hum, and finally environmental noise, which is extraneous noise from the sound field. Then we have broadband noise. The first example is pink noise. Pink noise is all frequencies from 20 to 20,000 Hz are playing with equal energy by octave. There's a characteristic negative 3 dB attenuation slope per octave. So what that means is that from 20 to 40, all those frequencies are at the same level. Then from 41 to 80, all those frequencies are 3 dB lower. Then 81 to 160, all of those frequencies are 3 dB lower than that. Pink noise is used for acoustic measurement and testing, and it represents the nonlinear functions of the auditory system, meaning that we don't hear all frequencies equally. This is an example of pink noise. White noise happens when all frequencies from 20 Hz to 20,000 Hz are playing with equal energy by frequency, and this is used to test equipment and systems. And we can hear the extra importance that the high frequencies are given in white noise. Frequency band ranges. So let's start with low frequencies, which is 20 Hz to 200 Hz. And this is what low mids sound like, around 200 to 800. Now the high mids are from 800 to 5 kHz, and this is what that band sounds like. Finally, the high band range from 5 kHz to 20 kHz. A high-pass filter allows frequencies above a certain cutoff to pass while attenuating those below. In this audio example, you'll hear the music unaffected, then switch to a high-pass filter. With the bandpass filter, these attenuate frequencies below and above a selected bandwidth. In this audio example, you'll hear music unaffected, and then a bandpass filter will be applied. We'll switch back and forth between these two selections. Low-pass filters allow frequencies below a certain cutoff frequency to pass while attenuating those above. In the following audio example, you'll hear the music track without the low-pass filter, and then the low-pass filter will be applied. Timbre is sound quality determined by frequency content and sound envelope. Remember that timbre is subjective. Here are 3 different examples of timbre. Now, the things that determine the timbre of that piano are the playing style, the way that the music is generated, the vibrations are generated from a hammer hitting the string, and it's also determined by the material that the instrument is made out of. Now, for a completely different instrument, we have a fiddle, which has its own unique timbre. And one more example. In this audio example, we'll go from a complex waveform to a simple wave, demonstrating how timbre can change depending on what harmonics are present. And in this audio example, we'll go from a simple to a complex waveform, demonstrating the same thing but in reverse. This concludes the first half of Lecture 8.